Okay, we're not finished quite yet with some of the basic stuff in Gateway C6, because although written separately in the specification, I hope that you would be able to recall the formula of certain substances like chlorine. So you've got chlorine in the spec, you've got hydrogen in the spec. We're going to write them all down here. Hydrogen, and oxygen and water, sulfates and chlorides, and so forth. So I'm going to give you an example of a few of them. Chlorine, hydrogen, oxygen, and water in particular are interesting because obviously when we're talking about fuel cells in a minute, those three is what provides the power. And then you've got sulfates. Sulfates, obviously sulfates are ions, sulfate ions, and they don't turn up on their own. And chlorine and chlorides are related in the sense that chlorine is a group 7 element, a halogen, and a chloride is, well, chlorine just as a halide, so it's a reacted halogen. And then there are sodium hydroxide and sodium chloride, obviously, so I'm going to talk about hydroxide ions as well. And I'm going to talk about carbonate and hydrogen carbonate. So we've got carbonate ions and hydrogen carbonate. Hydrogen carbonate ions. Oops. Then we talked about I've already shown you carbon dioxide. I hope that shouldn't really be a problem at all for anybody. Carbon dioxide, and we have got ethanol, ethanoic acid, and I'm going to leave them for a little bit later. Ethanoic acid, because they are, and glucose, they are organic compounds, and therefore they do form salts. Well, ethanoic acid does form a salt, but ethanol and glucose, obviously you just need to recall the formula for them, and not necessarily the structure as such, although ethanol is quite simple, and so is glucose actually. Okay, so hydrogen is just H2, oxygen is just O2, and water is H2O. And I've even shown you how you make water from hydrogen oxygen, and making hydrogen oxygen from water is just a reverse reaction. Sulfates are SO4 2 minus ions. Getting a little bit crowded there, but and chlorides are Cl minus. Hydroxide is OH minus. And again, I'm hoping that this is just refreshing your memory. And carbonates, hopefully you'll know what that's. CO3 2 minus. Hydrogen carbonate is essentially the same, except it's got a hydrogen in front of it, and that provides 1 electron in the structure, so the overall charge on the ion is just 1 minus. Carbon dioxide is of course not charged at all, it's CO2, and I hope that's not a problem at all. Ethanol, and I'm going to bracket them and leave them for a bit. Now if we make any structure with any salt with a sulfate, then again sulfates are SO4 2 minus. We just need to bear in mind what the metal ion is. So if we look at magnesium, or we look at tin, I'm just going to write the word there, because tin, the symbol is SN. It doesn't correspond to like magnesium, it starts with an M. Tin is SN. Calcium is mentioned in the specification. Iron 2 is mentioned here, and iron gets a Roman numeral because there are different forms of iron, but we're just concerned with iron 2 at the moment. So basically that will be iron 2 plus. It's missing 2 electrons, so the sulfate ion has got 2 extra electrons, and the metals on the right here are all missing 2 electrons after they've reacted. So what would the salts look like? Well, since the charges overall on a salt need to be balanced, i.e. 0, these react 1-to-1, or have reacted 1-to-1. So you get magnesium sulfate literally just being MgSO4, and then you can write all the other ones down if you really want to. And that's really it. It gets a little bit more complicated when you've got something like sodium, which is only 1 plus, and you've got sulfate, which is 2 minus. But you've got 1 positive charge here, and you've got 2 negative charges here, so how do you balance that out so that overall you get a compound with no charge? Well, you use 2 sodiums and 1 sulfate, and guess what? The overall charges are balanced out. And equally, if you've got hydrogen carbonate ions, that is 1 minus, and you've got sodium, you've got 1 plus 1 minus, wonderful, that just cancels each other out, and there we go. Or if you've got magnesium, then you've got 2 plus charges here, and if you use hydrogen carbonate, again you just use 2 of the hydrogen carbonates to cancel that out, and that correspondingly makes MgHCO3 2. So that would be magnesium hydrogen carbonate. Irrespective of the existence of these chemicals, you can make or compose anything that you want. They may not be stable or may have odd properties. That doesn't concern us at the moment. Okay, so I said I would leave ethanol and ethanoic acid for the moment. Well, ethanol should be familiar from such things as alkanes, in the sense that you've got ethane, the root ethane there, and if you remember your alkanes, then you've got methane, ethane, propane, butane, and pentane are the first 5. What does that mean, the first 5? The first 5 in the sense that this has got 1 carbon, this has got 2 carbons, and if it's alkanes, you remember CN, H2N plus 2. So that's C2 is the N there, so that's 2 times 2 is 4 plus 2 is 6, then it's that is C3H8, and so forth. But ethanol, basically, we've got 2 C's again, and in the structure, rather than having every position taken up by a hydrogen, because that would make an alkane, ethane, what we've got is we've got 1 position taken up by MOH group, hydroxyl group, and that makes it an alcohol. So if we count the number of H's, we can write it down 2 ways. I prefer to write it as C2H5, and then with an OH, because you can then immediately tell that it's an alcohol. You could write it as C2H6O, but then it wouldn't immediately be obvious what it was, and in fact it can mislead you. So that's quite a good way of writing it. If you've got ethanol, then you've got an acid group in there, and I'm just going to show you what that looks like in terms of organic chemical. So an acid group looks like this. It's often referred to as a COOH, COOH, and that's how you'd normally also write it. So you'd have CH3 COOH. So now you can see how that writes. What I would say is that don't be too sort of hung up about that at the minute. But what we need to be able to do at one point is recognize these structures in order to identify them. Then finally there is glucose. And glucose, I'm not going to spend very much time on at all, because everybody knows that it's the product of photosynthesis. Carbon dioxide and water go in, oxygen, glucose come out, and that's basically the structure C6H12O6. It's maybe just good to recognize that there's quite a lot of oxygen, and or if you want to look at it another way, I've already rewritten it before as C6H2O6, so you could look at it in terms of there being water in it. And if you add sulfuric acid and sugar into a beaker, so you've got your sugar there and you're adding the sulfuric acid on top there, the sulfuric acid has a strong tendency to rip out the water from the sugar, and what you get is like a column of carbon with a lot of steam coming off, and it grows into a big sort of column of carbonaceous carbon material, charcoal essentially, and with the steam coming off the top. And the steam obviously is the heated water that was in there. And the water that isn't steaming off gets ripped out by the sulfuric acid. So when we use the only other thing that you need to do is balance equations using displayed formulae. So displayed formulae are, when I showed you that before, I display all the bonds. So that would be methane, for example. And if you said, okay, combustion of methane, how does this work? Then you can add oxygen, and since it's all displayed, you would then get CO2, and you would get H2O. I mean, I'm displaying everything now, so more normally you would probably get the methane, and then you'd have to count the C and the H's, balance that. For every carbon in complete combustion, this is the trick here as well, complete combustion, where there's an excess of oxygen, you get 2 oxygens used up, so 1 O2 molecule, and for every 2 H's you'd use 1 oxygen atom, so there are 2 pairs of hydrogens here that would make 2 H2O, so that would mean 1 oxygen molecule will get used there, and then every carbon uses 1 whole oxygen molecule, so you get that balance really quickly. Okay, so let's check. 2 times 2 is 2, plus 2 more is 4. You've got 2 times 2 oxygen atoms, 4, 1 carbon, 4 hydrogens, and 4 hydrogens. In balancing, once you've balanced 2 elements, the third one is usually, if there are 3, if you've balanced 2 out of 3, or 3 out of 4, then the other one, unless you've made a mistake somewhere along the lines, it's balanced itself. Okay, so now we're getting into the really new stuff out of C6, and I'll see you in a second.